Today I'm going to talk about compositional zero-shot learning. This is actually, I would say, a task that has been raised a bit of interest in the recent years. And it has a lot of challenges, as we will see in the talk. So I will briefly mention what is a compositional zero-shot learning, so an overview of the task. Then we will talk about why we should care about this task and what are the motivations and actual practical applications. We will then go to a review of the literature in this task, and then I will talk about two works that came out from our lab recently. One is on using graph embeddings for addressing this problem. Then I will briefly mention what are the open problems actually in this in compositional zero-shot learning. And then I will talk about how we try to first attack one of these problems, which is the open world scenario. And then I will talk about some conclusions and future works. So first, let's start with what. So what is compositional learning in general and compositional zero-shot learning? If you go in the literature, it's really huge, the amount of information and definition you can find about compositionality. Here I took just three of them. The first is what is called the principle of compositionality, which is roughly stated as the meaning of a complex expression is determined by the meanings of its constituent expression and the results used to combine them. This is called the Frege principle, which is actually has been stated differently at the time, and maybe it dates back to Boole also. But the main principle here is that you have a wall that is composed by some parts, some basic concepts, and then you want to, by combining these basic concepts, you are able to represent the whole, the full complex expression. Later, other researchers stated it in a different but similar way. This is from a paper of Schmid-Huber of 1990, and this is here the main message is if you have a task, you can actually decompose it into a sequence of small subtasks, and then you can solve them to achieve your final goal. And this is what's generally known as divide and conquer strategy. Another one that is more poetic, and I like it, is this from a recent paper of Yuil, and it states that we can tear things apart, comprehend them, and mentally recompose them at will. This is what is compositionality. Now, compositional learning obviously is a vast field, and I think that most of the approaches there try to really model this fact that you have some primitives, basic concepts, and that you want to learn how to compose them to maybe solve some task. Or you can even learn actually how to detect which primitives your full complex image, object, or whatever you see is made of, and then once you have detected these primitives, performing some other tasks. And this is actually what's the exact goal of compositional zero-shot learning. Because here, what you have is that the primitives are some states, such as wet, dry, old, and then you have some objects that are other kind of primitives, so dog, cat, and car. And during training, you see just some combinations of those in terms of images. So every image represents a combination of these primitives. And what you want is to learn a model that is able to, at test time, generalize to possibly unseen compositions of these basic primitives. So here, for instance, we have a dry dog or an old cat, a wet car that weren't in our training set at the beginning. So this is actually if we go back to the definitions I gave you before, is something a link to detecting what are the primitives. So we have the wall that is the image, and we want to understand which are the primitives that build up this image, and eventually be able to recognize these primitives even when they come with compositions that are actually not present in our knowledge base, let's say. So this task is pretty challenging because the way the states modify an object is not trivial. So if you take a tomato and a banana and they are unripe, if they become ripe, actually the way they become ripe is pretty different. And similar, if you take the state dry and you apply it to a car or a cat, and then you go with a wet cat and wet car, and the outcome is completely different. I mean, the car is not furry, and so it cannot look like a cat in this sense. And this is why it's hard to model really how what is the consequence of changing state in an object, because the way a state changes the representation of the object changes among objects themselves. So it's not trivial to learn how to compose state and objects. Now, maybe the task seems quite simple, but of not that practical interest. But I don't think so. And an example can be this. So let's suppose we have a human that interacts with a robot, and the human calls the robot Marvin and wants Marvin to prepare an orange juice. And now Marvin wants to help the human and goes for preparing the orange juice. And then Marvin goes to the kitchen and finds these oranges, but also these other oranges, some moldy ones. And we need to be careful, because if Marvin picks the wrong oranges to prepare the orange juice, maybe the effect on the human is not that funny, and we would like to avoid it. So this is obviously was a made-up example, but I think it's not that unrealistic, in the sense that we would like an agent or whatever acts in the real world to understand not only the object it sees or it needs to recognize, but also the state of the object, because that changes the way the agent needs to interact or make decisions when acting in the real world. And another example, for instance, is if you find a road like this or a road like this, you will drive in a different way, because of course you don't want any sheep to be injured in the process. And also, if you want to hug a dog, probably you would hug this dog and not this one. You would like kind of act differently with respect to the actual state of the dog. So another thing of this task is the zero shot. So why shall we care about the zero shot setting? This is something that actually comes from how the data in our world is structured. So we have a vast amount of compositions, and the number of images per compositions is actually long-tailed. So maybe we will have a lot of images of wet cats, dog, and ripe oranges. But probably we would have less images of moldy oranges or muddy dogs, because, I mean, we don't tend to take pictures of things that we may dislike, such as moldy oranges. And maybe there are some very rare states for these objects, like, I don't know, a cat climbing or a weird huge dog. And for those, we will have very, very few images, and we cannot really build a dataset containing all possible compositions in the real world, and with high number of images per composition. And one thing that I would like also to mention is that from a research point of view, without the zero shot, it would be probably not a super interesting problem, because it ends up being a classification problem, while here you can you want to generalize to new compositions of your basic concepts, which is much, much more interesting. So now the next point is how. I hope I convinced you I explained enough well what is this composition zero-shot learning task and why we need to care about it. Now I want to talk a bit on how we can address this task. And in the literature, there are different works, but the very first basic strategy is what's called visual product. And this is actually is the first way one can address this task. It's very straightforward. So you take the image and we can extract some features out of the image. And then from the features, we can predict the state and object independently. Obviously, this is, as I said, straightforward as approach, but doesn't model actually the fact that state and object are actually depending on each other, as we have seen before on how, for instance, wet modifies a cat or a car, and similar for ripe, banana, and tomato. And so this treats state and objects independently. But it's a good already baseline, like it's something that is plug and play, can be applied to this task pretty effectively, but misses this fact of modeling how the compositional space and features of images in this compositional space should actually are actually represented. To try to model this in a more let's say sound way that tries to model how state and objects interact with each other. A good approach, a first approach in this direction was LabelEmbed that was proposed in 2017. And this approach, what does is that it takes the still extract features from the image, but it takes the state and object embeddings, or in that case were classifiers, weights of the classifiers for the state and objects, and then mixes them through a transformation. And then both the image features and the new embedding obtained by transforming the state and object compositions are projected into a shared embedding space, together with this yellow dot is the embedding of another composition. And then a loss is minimized, like a cross-entropy loss, or it can be a triplet loss, and you want basically that image features of the image features are closer in this shared embedding space to the corresponding embeddings of their compositions. So if this purple dot is the wet dog composition transformed and projected in the shared embedding space, you want it to be closer to these image features with respect to, I don't know, ripe banana or any other compositions you have in your compositional space. This concept actually is simple, but can be expanded, and actually works did that. For instance, in Task-Modular Networks, the transformation is modeled through a gating function. So we have a shared network, which is these M modules, and the modules are activated through gates, and the values of these gates are computed through a gating net. And the input to the gating net is the object and its corresponding state. And we hope that in this way, we can compute a classification function. In this case, it's not a projection in a shared embedding space, but it's more a compatibility score between the image and the parameters of this task-modular network. And we hope that the getting function really is able to capture if the image represents the concepts that we use to condition this getting network. And this is trained with cross-entropy loss. And it's actually a general idea, because what you do is that at the end you are generating the parameters in this case, mostly connections, but you can actually generate parameters for each of these compositions that you want to recognize. And this has been explored also in another work, which is task-aware feature embedding networks. That is actually a more general approach for also few-shot learning. And in this case, what you have is that you have these task encodings, which can be your compositions. Obviously, one thing that I forgot to mention is that this can be binary, but can also be word embeddings, as most of the approaches use, or classifiers of these basic concepts. And what you do is that you use this input to generate some parameters that you apply on top of image features to get a score. So the score represents the compatibility between the image and your actual task, that in this case are compositions. All these approaches, I find them interesting, and but there is one thing that actually it's even more interesting, at least this is what I personally think, which is modeling the fact that we are in a compositional space. So it's not that simply we want to combine the state and the objects, but we want also to enforce that our compositional space has some particular properties. And this is indeed the next part that I want to talk about. So how we can enforce some particular properties into our compositional space. And probably the first work going in this direction was attribute as operators in 2018. And the idea behind this work is that if you take objects, the objects are actually, you can visualize an object. I mean, if I tell you to imagine what can be a prototype for the car object, you have in mind that maybe this, it's a good prototype for an average car. But if I tell you what's the prototype of a state, an attribute, which is sliced, it's a bit harder to imagine. I mean, because it really depends on what you slice and how you slice it. It's really hard to define. And so what the authors proposed was to treat objects as vectors and states or attributes as operators. So the attributes are modifying the representation of the object. And how it is implemented, well, basically you have, as I said, vectors representing your object instances. And these vectors, again, can be word embeddings or whatever semantic representation we may have available. And then there are matrices that are learned that map the objects to this shared embedding space. Again, you have the image projected here, and then you take the object representation and your state operator matrix, and you project everything in the shared embedding space. And you want to minimize some sort of loss, in this case, triplet loss, to make sure that images and their corresponding compositional embedding are closer with respect to any other random embedding. One cool thing about this is that since now states are operators acting on objects, you can really enforce that these operators are doing the right thing in the compositional space. What do I mean? Well, you can enforce different properties. The first, of course, can be that if you take that is the joint representation of sliced and banana, you're actually able to predict both sliced and banana independently from this joint representation. Another thing can be the inverse. So if you take something, this f of x is an image containing an object that is sliced, and you take out the sliced state through this matrix, the inverse of obviously the sliced operation, and then you add the ripe state, you should obtain a vector that is close to ripe banana with respect to sliced banana that was the starting point. And you can do the same in different ways. Like you can act at the level of antonyms. So if you start with a banana, you make it ripe, and then you make it unripe. You should go back to the original banana you started from. And similar, if you go to the, you want the states to be commutative. So if you take a banana and you slice it, and then you want it to be ripe, you should obtain the same vector that you would obtain if starting from a banana, you make it ripe and then sliced. And this is like pretty interesting because models what we think this compositionality should behave in this space. Like now we know that if we make states interact and modify an object, we would obtain something that at least for us makes sense, like this commutativity or inverse transformations. This was an example, and actually this kind of approach was taken also in other works, such as SymNet. SymNet models it through actually from a different perspective, which is symmetry and group transformations. What I mean by that? Well, if you take an apple and you want to add the state peeled, you would obtain something like a peeled apple, hopefully. But if you take a peeled apple and you add the peeled attribute, a peeled state, you would not modify your representation because the apple is already peeled. And similarly, if you take an apple that is not peeled, and then you take out the peeled state, you would still be on the same apple because the apple was not peeled to begin with. And this is actually the overall idea, like having a modeling how, again, a state should modify an object, but also taking into account when both the the object should not be modified by the state because maybe it doesn't contain that state, and so you cannot take it out, or the state is already included, and so you cannot add it again. And based on this principle, they define different losses, which is actually, as approaches, the idea behind the approach is similar to what we have seen for attribute as operators. And it's as you can see, there is already the commutativity that we have seen before, the invertibility, the identity. So when you don't modify your original transformation, there is also this closure that actually is interesting. So it's basically you take an apple, you add peeled, but then if you have a representation of this peeled apple and you want to add peeled again, you will end up in the same representation, which is what I tried to explain to you before. And the one thing to notice is that here the first thing that is predicted is actually the object. So it's not that object and states are predicted all together, as maybe in attribute as operators, but you first predict the object, and then you check what is the attribute that has been the state that has been applied to this object by this relative moving distance, which means that you start with your representation in this embedding space, and if you add an attribute and you have a small distance from the original projection that you obtained from the image space, that means that probably the attribute was already in the image. So you are not modifying your embedding by adding this attribute. And similar, if you take out, if you take out something, I need to apologize actually because I did it in the other way around. So if you take out something that was in the image, you expect it to to be very, very large in the distance in your embedding space. Well, if you add something that was already there, the distance should be low. And okay, yeah. So I'm super sorry because it's actually I got confused. But the idea is that, so if you take one single state and you check two things, you check what is the impact of adding that state to the representation of the object, and what is the impact of taking out the same representation from the object representation that you obtain, where this green is actually the projection that you have from the image. So if you add this attribute and the adding this attribute doesn't move much the representation of the image, it means that probably the attribute was present. And so if you take out the same attribute, the distance now grows and is large. And you can compute this D plus and D minus for every object in your dataset, for every state, sorry, in your dataset. And what you obtain at the end is that if you can check the difference between adding and removing an attribute of these distances obtained from adding and removing an attribute, and if the distance that you have obtained by adding it is less than the distance that you obtained when you have removed it, it means that probably the attribute was present in the image, while it was not present in the other way around. Again, I'm super sorry I confused you because I was representing in a different way, but I hope you get the point. Like, of course, if you have a peeled apple and you want to add the peeled attribute, you are not actually changing its representation. But if you take it out the peeled state, now your representation change abruptly. While maybe if you take the same apple and you add the ripe, you add the unripe state from this red apple, probably since the apple is ripe, your distance when adding the unripe state, it will be very large to your original embedding. While if you remove the unripe, the distance will be small because unripe is not something that is not a state of this apple. And this is what this approach does. I hope I gave you the idea, the overall idea. This is actually a very performing and pretty good method for compositional zero-shot learning, enforcing both the properties that we want in the shared embedding space, but also modeling inherently how objects and states should relate and modify each other.
Yeah, this was very clear.
Thanks. Sorry.
Thank you.
So the last work I want to talk about, and I think the first author Yuval is in the Zoom, so please correct me if I say something wrong, is a causal view of compositional zero-shot learning. This is another very cool work that came out recently at New Rips, and in this work, actually, the property that we want to enforce is something different. So if we have an attribute and an object characterizing a composition, we are inherently biased to the compositions we saw at training time. A cool example is that if you have black eggplants, and maybe as vegetables we have only eggplants that are black as same categories in your training set, then if at this time you see, I don't know, a black tomato or something like that, you will probably classify it as a black eggplant because it's the only vegetable that you have seen as black. So we cannot ignore the fact that there are correlations between attributes and objects. And one thing to improve the generalization of the model is to actually enforce that the attribute and objects are independent of each other. We want to take out, let's say, this correlation. And the basic idea indeed is this. So to enforce, to have a representation of the object and a representation of the attribute that are independent, but actually that when they are composed, they can give back our image. So that we want to model what originated this image. What are the causal factors that originated the images, and with the factors being the states and the objects. And to do that, this is achieved with different losses. One cool one is that if you take the image and you want to retrieve the attribute, you should obtain something, an embedding that is closer to the embedding that you obtain for the attribute, and the same for the object. And then there is a loss also enforcing that these representations are actually independent. So in such a way that they don't kind of interfere with each other. We can take out this correlation and hopefully generalize better at test time. This is the last work actually I will talk about, because now I want to consider another thing, which is what about the dependency between the compositions? So for now we have seen just works that tend to make the state and objects interact among themselves, shaping either the compositional space accordingly, or building classifiers that take into account how to compose the primitives. But maybe there is something more that we can take into account, which is the dependency that occur between seen and unseen compositions. And the overall idea is something like this. If we have as seen categories, maybe wet dog and dry cat, and then as unseen one, we have a wet cat, we can use the feedback that a wet dog and dry cat received during training to obtain a better representation for wet cat also. And this is something that is treated in a, let's say, intrinsic way for the implicit way for most of the works, in the sense that what we add is that we hope that either the transformations that we obtain or the projections in the compositional, in this shared image and compositional space that we obtain kind of already model this. But it would be interesting to enforce this link between seen and unseen categories explicitly already, either in the model or during training. And this is the idea that on which this work, Learning Graph Embeddings for Composition Zero-Shot Learning, is based on. This is a work of Ferjad, Yonchin, Federico, and Zeynep that has been published now in CVPR. And this work models the dependency among the compositions through a graph. So let's suppose you have this space of state and object representations, and that you have these compositional versions of them. So all the dog, cute dog, etc., etc. Now, what we can do is to connect both the primitives and the compositions. And so for connecting the primitives, we can connect old and dog, since we see that old dog is something that was that is contained in our training set. And also we can connect, for instance, we can connect the dog to old dog, because it's given. The primitives are connected with every compositions they build on. And why this enforces that some feedback flows from seen to unseen composition. So here we have, as unseen is a cute dog, if I remember correctly. We will check later anyway. So, what we obtain is that whenever we update the vector of the representation for dog, this is something that influences cute dog. And again, this happens also for the cute vector. And this actually is built on 2 levels. So the first level is with this connection. In the second level is because these connections interact through a graph convolutional neural network. So what we have is that we have an input graph, and we have a graph convolutional network processing the features of each of the nodes in the graph, where the nodes are actually both the primitives and the compositions. And so we have that each of the compositions is in the first layer of the GCN. The compositions are influenced only by their own states and by their by a self-connection that connects the composition embedding to themselves. But in the second layer already, since the attributes and the objects representations are influenced by the compositions as well, we have that when we recompute the vector of cute dog in this case, we will do it with a representation of dog that has been updated according also to old dog, and a representation of cute that is updated using also the representation of cute cat. And this is how seen and unseen compositions interact, because we have a graph, and in the multiple levels, all the nodes in the graph exchange information. So at the end, what we hope to obtain is something a refined representation of each composition. And we hope that by projecting this unseen, this refined representation in the shared embedding space, this is actually better and captures better the relationship among the compositions and the respective visual features than just not taking into account this kind of latent dependency among each of the compositions. And this approach was actually trained also end-to-end. As I will show you in the result, this is not something so straightforward, because it's at the end a zero-shot problem. So there is always the risk to overfit to the seen class representations and not be able to generalize to any unseen one. But by enforcing this graph, so this dependency among primitives and compositions, this graph imposes a kind of structure in the compositional embedding space that then allows the network to better generalize also to unseen compositions at this time. The training is actually pretty simple, because it's a cross-entropy loss on top of the compatibility score, which is a dot product between the embedding of a composition and the embedding of the respective image that we want to classify. And also the inference is just the argmax of this compatibility score. So looking at some results, actually there are another contribution of this work is not only the methodological, but is also dataset related, because there are two main datasets for composition zero-shot learning in the literature. One is mid states, where you have 245 objects, 115 states, and those are obtained from images downloaded from the web. This means that it's not super cleaned, because as you can see here, like this old bike is actually mixed in a lot of other stuff. So it's hard to say that this image belongs to an old bike. Or even here, diced apple, there is a diced apple, but it's mixed with other objects. But it's still a large benchmark. At this time, you will be classifying both seen compositions, in this case that are 400 seen pairs, and 400 unseen compositions. So it's really challenging. Another dataset is UT Zappos, and here actually you have 12 objects, which are shoes, and 16 states, which are actually mostly related to the type of shoe. And this is a dataset that was built for other purposes, actually, like fine-grained recognition, then also sketch-based image retrieval, something like that was used for that. And in the context of compositional zero-shot learning is a bit unclear if all these compositions is something that actually we can model with our methods, because some of them are related to the material. And I mean, I'm not an expert of shoes, so for me, sometimes it's hard to look at an image and recognize the material of a shoe without actually touching it. And so this is one reason why it was proposed, this new benchmark, which is Compositional GQA. This is a new dataset with 870 objects, 443 states, and this is has been obtained from the GQA dataset, which is a visual question answering benchmark. And this data set actually is the largest now available, because it contains really a compositional space that is much larger. I mean, we have almost 1,000 of objects, while in mid states we had 250 almost. And same for the states. And at test time, you will see 1,000, more than 1,000 unseen compositions. So it's super, super challenging. And it was built using the bounding boxes and the descriptions of the GQA dataset. So it's much cleaner with respect to just downloading images from the web based on queries. So how do we measure the results? There are multiple ways, and the metrics that we will look at least in these slides, are the area under the curve, under the seen and unseen accuracy curve. So you want to see how varying a bias on the prediction of unseen classes, because of course all of these methods tend to be biased on the seen compositions that they have seen at test time, as it happens for generalized zero-shot learning methods usually. You want to add a value that rises the scores for unseen categories, so unseen compositions in this case, and you want to see how your harmonic mean varies in this scenario. And so this is the first is the area under the curve. Then we have the best harmonic mean taken out with the best bias. You can see look at seen composition accuracies and unseen composition accuracy. You can also look at state and objects separately, but it's not done in most of the works. And so here I will report just R under the curve and these other metrics. And these are the results. So what we can see is that this graph-based approach is actually very powerful. Even this is the version not end-to-end trained of the approach, and already in terms of AUC on both the validation and test set, the performances are much higher than previous work in mid states and in C-GQA. This doesn't happen much in UT-Zappos, where Task-Modular Network is much more effective actually in terms of AUC on the test set. But actually, as soon as you fine-tune the network end-to-end, the performances are pretty high and surpass all the other approaches in all benchmarks. It's also like nice to see the unseen accuracy and the best harmonic mean, which are actually what give us the measure of how practical are these methods for predicting unseen compositions at the end. And it's the performances in the C-GQA benchmark, where the unseen compositions are 1,000, are remarkable. Like in the unseen case, one goes to 100.7 unseen accuracy, 14 by end-to-end training, while the best Bayesian is SymNet with 9.2. And a cool thing now is to see what is the actual impact of this graph. And the first Bayesian is direct word embedding. So it's not using any graph. It's just taking the word embeddings and putting them in the shared embedding space. And by refining them by just training them independent. And this is achieves a 5.9 AUC in the validation set of mid states. But as soon as you include the graph, this AUC grows to 7.6, while the best harmonic mean is already is still lower. But if you have also the self loop that obviously takes into account the fact that a composition should influence itself, and this applies. This is more important also for unseen compositions, because otherwise their embedding will not influence well, let's say, the seen representations, and then the discriminativeness that we obtain for the unseen composition is a bit less. The best harmonic mean grows. And if you include also the state object connections, we have another improvement. And a cool thing is that we can even include other forms, like infer our connections also from external knowledge, such as WordNet, for instance. But this, in this case, didn't improve the actual results.
So if we can ask just a question about the
Yep.
graph, also Ina had, I think, a similar one to the one I have. How is its structure set? Is it humanly defined? Is it learned?
The graph itself, the connections are derived from the data sets. So maybe it's better to see it here. Like in our data set, we have a set of seen and unseen compositions. And we know that there is cute dog, for instance. And so what we can do is that, okay, since we have cute dog, cute and dog are connected. And then we can connect dog with cute dog and cute with cute dog, and vice versa, because this is a composition that exists in our training set. This is how those compositions are built, and are built for both seen and unseen compositions, because otherwise, like there will be the graph that is dynamically built, and it's not that easy to make it generalized to at test time.
How can it be built for unseen compositions?
Because there is a prior, and it's something that actually we will talk also about later, on the unseen compositions that will be seen at test time. This is something that actually not all approaches assume. In this approach, it's needed because otherwise the graph, there will be no actual feedback from seen to unseen compositions, and the power, let's say, that is beneath this graph will become less. And I mean, actually, there are also results, I don't know if are in the paper or in the supplementary, that without building the graph with unseen compositions, the performances are not that great, because actually you don't have this feedback.
So actually, every connection here on this graph has like a description if it's seen, unseen, right?
Actually, it's agnostic to the type of composition. So it's not that, for instance, here all dog is assumed to be unseen, and it's not that the connection between dog and the old, or both of them to the compositional dog, changes because the composition is unseen. Those
And
are the same.
And are the connections deterministic or probabilistic?
Are deterministic, so they are just set to 1.
Okay, and also, so you mentioned there's a priori, so I guess they're not built like manually built, but somehow derived during a process. I don't know if it's the training process or something before the training process.
No, it's actually, they are manual, in the sense that you have your data set, and in your data set, you know that there are these compositions. And so for each of the compositions, you can just say, okay, since in my training set, I have cute dog, cute and dog are connected, and those are connected to the...
Of course, because this is the seen one, that's easy. But about the unseen one, where we have some a priori.
Yeah, you have also a list of unseen classes, of course, when you test your model. Like with your data set, you have a campaign descriptions for them. But actually, this is like you know the list of unseen compositions. But this is actually a clear limitation of the approach, and it's a limitation also for any method applied to composition zero-shot learning at test time. because at test
Okay.
time is not that you predict anything that is not in your set of unseen test unseen compositions. And yeah, this is a problem, and I will actually expand on this later.
Okay, just to like to explain my side, maybe our side of from the people listening, it's currently a bit hard to imagine how you define a connection between, let's say, cute and cat.
Yeah.
How does it working, and what's like, if you'll say, let's assume there's a taxonomy categorizing cats and dogs a similar fashion, and we know that cute applies to that taxonomy, and it's all predefined, and it's okay. But like the way we have it right now, it's a bit hard to understand what's going on with the graph because of it.
Okay, like the maybe the simplest way to explain it is that it's not something generic. Like it's not that you have to infer the states that can be applied to an object, but your dataset, your benchmark will come available with a list of compositions. This is like anyway, this is something that you need. You can infer it from the labels of your training set. And of course, in the dataset, there are both validation and test pairs. And so you know all the compositions that are available in the say this word that is your dataset. So in your dataset, let's say that your dataset is this, you have these 4 compositions. And so you build every connection based on those compositions. For instance, an example here is that there is no old cat in these images. So it seems that old cat is not a composition in the dataset. And as you can see in the graph, old and cat are not connected. And cat is not connected to any composition because we are missing the old cat composition. It's not a part of the dataset. And this is the basic kind of or reasoning. Like any composition available in the dataset is used to build the graph. If something is not within the dataset, is not used to build the graph.
But again, the unseen compositions are not within the data set, and still they're used to.
Are inherently within the dataset because
Inherently?
yeah, like your dataset contains validation and a list of unseen classes. I mean, any method, both in zero-shot learning, standard zero-shot learning, and in composition zero-shot learning, needs to know what are the unseen compositions. Otherwise, you cannot build a classifier for them. Otherwise, I mean, you don't know what to predict at this time. So you would need a list of unseen composition that you are interested in, and based on these unseen compositions, you can then use them to build your graph. You don't have images for those, but you can build the connections and use them during training. This is the idea.
So there's like a sort of a small bias implemented in training.
Yeah,
okay.
It's something that is actually again not new in zero-shot learning, because in zero-shot learning, at the end, if you want to predict unseen categories, you must know which are the unseen categories. Otherwise, you will not predict them. Or you assume that you want to predict the whole possible concepts present in the word, which is something pretty hard to do. So you need to know the restricted space of composition or compositions in this case, or categories, unseen ones, that you want your model to predict at this time. But this must be known a priori, like before employing your model in the real world. Otherwise, the model will not predict those classes, or we will not, can also not include them in the output space. And having this knowledge can be used also at training time in principle. In zero-shot learning, a lot of works did that. In composition zero-shot learning, I'm not sure. I think maybe this is one of the first using this knowledge, but allows you to propagate information between seen and unseen categories, even without images of unseen categories, which is like the cool stuff that you want to exploit.
Okay. And Ina had a question. I'm not exactly sure. I'll explain what I'm not sure, but she asks, if introducing the graph improves results as the number of scenes grow. And I think she's meaning scenes during training time.
Yeah, yeah. This is an interesting question, and actually, I don't know. I don't think I can answer, because it's something that, like, not being an author of the paper, I didn't try myself. I would need to ask Farjad. I think that the improvement will surely be there. Like, anyway, if you have more scene categories, your model will improve, because it has more knowledge that it can use to then generalize to unseen composition. But this is true for the graph method, but also for the other compositional zero-shot learning methods, because it's the more scene categories you know, and the better is maybe you learn your transformation from the primitives to the compositional embedding space, or whatever your method is doing. Like, the more scene categories, the more training data, variety of training data you have, and the better is the model. If the graph and the unseen accuracy of the graph has a clear benefit from having more a clear benefit, let's say a clear relative improvement with respect to other methods by having that, actually, I don't know, I cannot answer. It's I would I mean, I am happy if we can get in touch also with Farjad, which is the first author of this work, and check it. It's a super interesting question, actually.
Okay.
Are there other questions from?
Not that I saw. Let me double check. No.
Okay. Yeah, I hope answered clearly, but feel free to anyone to stop me, let's say, and ask clarifications for everything I'm saying. So we were here, like the fact that maybe since the graph is limited to what is present in the training set, in principle, we can also connect other things by using external knowledge. In this case, was used the word net hierarchy, but it didn't bring particular improvements, and probably something that needs to be studied and investigated more. This is a thing that I mentioned before. So this fact of having the end-to-end training working, and I mean, looking at the results, one can say, okay, it's the method is working better just because there is the end-to-end training involved. But if end-to-end training is applied to other approaches, this is mid states, and as you can see, TMN and SymNet have a 3.5 and 4.3 AUC. If those methods are end-to-end trained, actually their AUC is not improving. And this is something that is coming from the fact that the graph that is built enforces a kind of structure in this compositional embedding space that allows to regularize the representations learned there. Another thing is like how the performance change with respect to embeddings, and actually the power of the method is invariant with respect to the input embeddings used. At the end, like word2vec was used for Zappos and C-GQA, and their combination for mid states, and the combination, sorry, of fastX and word2vec for mid states. Finally, here are some qualitatives, and the qualitatives I can show you that in this case, like given an image, what are the 3 top compositions predicted by the model, and as you can see, like they kind of make sense. If you look at the elephant, you have that small elephant that is the label of the dataset, is the first one, but the second is tiny elephant. So the network has kind of recognized that this elephant is small and also young, and similar also to this cat. Maybe I'm not sure that this cat is young, is unclear from the picture, but it can be wet, and it's anyway a tiny animal, and wet cat was actually the ground truth. And the model can be applied also for retrieving images. So given a composition, I can produce an embedding of the composition and checking which are the images that best fit this this compositional embedding. And I mean, the output kind of makes sense. Like old cars are cars that are either old or kind of rusty and weathered. I don't talk about shoes because I'm super ignorant, but I mean also the walkway seems to be reasonable. So now the next part is if we are done with composition zero-shot learning now, and the answer is no, of course. And the first problem I want to highlight is this. So let's if I give you this image of a dry cat, I would probably also say that this cat looks young, arguably, but I think it's young. I find it cute personally, and maybe the cat is sleeping. So it's unclear which state we should give to this cat. And so a clear limitation is this fact that objects come with multiple states and with and maybe you may have an image with multiple objects as well. And it's limiting to predict just one object and one state per image. It's limiting and probably not that practical in reality as well. And the second limitation actually is linked to what we were talking about before. So if we take mid states, you have all these states and objects, and similar for Zappos, C-GQA, and at test time, you classify, you have an output space that covers all scene compositions, and those, I mean, you know that they exist because they were in your training set, and the unseen compositions, for which someone told, okay, look, there are these unseen compositions at this time that you would like to recognize. And these are 1,262 for mid states, 101 for Zappos, and for C-GQA, almost 8,500. But these actually represent just a tiny bit, not for Zappos, but for mid states and C-GQA, we are actually looking at a tiny portion of the full compositional space. And for full compositional space, what I mean is the product between these two numbers. I mean, I know that like even if we see the qualitative examples here, maybe, I mean, you don't have a broken cat. This is true, but actually, how can you know it a priori unless someone gives you this information? And so this is actually what we focused about in the next work, because it's not only the fact that these weird compositions like broken cat are present in this full compositional space, but also some other compositions like cute cat, a small cat, that we know that they are kind of true for existing in the real world, but if we look at the compositions in mid states, they are not present in none of the splits. And this means that a compositional zero-shot learning model built on mid states, as it is, will not predict them at test time. And this is a limitation because, of course, in the real world, we may see cute cats and small cats. This is what I call the closed word assumption of these models. And in what I'm talking about next is actually a work I co-authored with Ferjad, Yanchin, and Zeynep, and we wanted to go beyond these limitations. So we wanted to work in the open world, where we take as output space the full compositional space. So we don't take percentages, but we go for the 100% at this time. This is challenging. This is super challenging because, I mean, if you have training compositions and unseen test compositions in a standard composition zero-shot learning, you have other compositions, like many more compositions that you didn't consider a priori, because, I mean, if you don't assume any prior, you cannot detect this set of unseen test compositions, but you have to assume that all compositions of state and objects may be available at test time. And in this case, there are both these unseen compositions that may be confusing for the model. Like now, since you have a ripe tomato, you maybe need to be careful when predicting a ripe apple. But also there are these weird compositions like ripe dog, airy apple, for instance, that obviously do not make any sense, but they are still present and they may be distractors for your model and making its performance even worse. And yeah, this is actually a challenging setting. And even in zero-shot learning, there are few works exploring this. And in zero-shot learning, what you do is actually that you take, I don't know, a vocabulary containing a lot of categories, a lot of names of objects, and you say, okay, now my full vocabulary is my set of unseen categories I want to predict at this time. Here for compositional zero-shot learning, actually things are a bit simpler to define because we have a set of objects, we have a set of states, and we just say that we don't restrict the space of compositions. Like all compositions are considered to be possible candidates at this time. I hope I gave you the intuition of the task. And now I describe how we started solving this problem or addressing this problem, let's say, far from being solved. So if, let's say we have an image, we can predict it, extract some features that are projected in this shared embedding space, where we also take state and objects. We extract some representations for them, which actually are word embeddings in our case. And then we learn this transformation function, similar to what LabelEmbed was doing. And we project these compositions here in this shared embedding space. And this is like the model we kind of propose for the standard composition zero-shot learning, and is our starting point. So here, what we do then is that we compute the cosine similarity between the image features, the image embeddings, and the compositional embeddings, and that then we use them to score, let's say, the compatibility between the image features and each of the compositions, and we can compute the standard cross-entropy loss and train our model with that. And we actually trained, we didn't try training it end-to-end, we just went for this transformation, and also we trained the word embeddings. So the embeddings of state and objects independent. Now, the problem is that maybe in the open world, we will have some other unseen composition that we didn't take into account, which is this, for instance, ripe dog. And eventually, we may have that our prediction now is wrong because ripe dog has a cosine similarity. The embedding for ripe dog has a cosine similarity with respect to wet dog. This is obviously an example, but it may happen with any of the unseen compositions present in this huge search space. So how we tackled this problem was to think about the feasibility of the compositions. And what the feasibility, what I mean is the probability that a composition is actually true, existing in the real world, and not just invented, let's say. And suppose we have a score. I will then tell you how we compute these scores, but let's suppose we have a score that tells us what is the feasibility of each of these compositions. And let's assume also that this feasibility are between -1 and 1, so in the range of the cosine similarity. What we can do is two things. So the first is thresholding these feasibilities and saying, okay, now from my output space, I take out everything that is below a certain feasibility score, and I can just, eliminating it from my output space. And so I restore like a kind of more friendly, let's say, output space at this time, where I'm taken out possibly a lot of compositions because are deemed to be unfeasible, and the problem is simpler. And another thing that we can do is actually softer. So saying, okay, I don't want to take out a priori any of the compositions because maybe this is too abrupt and I would end up eliminating something that is wrongly estimated as unfeasible. And we can apply a margin-based loss. And what I mean by a margin is that we have the same cross entropy as before, but now the probabilities, so these scores, are actually changed. It is 1 to the probability because are actually the cosine similarity scores. And also I'm summing up the denominator not only on the syn categories, but also on the full composition space. Like now we have no prior assumption on the unseen compositions. We are extending the model to take into account any possible compositions in the word, where the word is actually the state and objects present in my dataset. And I define the scores as the cosine similarity between image features and compositional embeddings for the training seen compositions, while for any unseen compositions, we add this margin to this bias, let's say, to the cosine similarity with a minus sign. This bias is actually the feasibility score of the composition. And we have a minus sign because what we would like to obtain is that if a composition is unfeasible, its score should be higher in such a way that when we train the network with the cross entropy loss, the network tends to reject this composition. I mean, it's unfeasible. We want it to not be predicted, and so we raise its score. So it's more penalized by the loss function. On the other hand, if actually this the feasibility score for a composition is positive, so the composition is deemed to be feasible, this minus is lowering down the score of that composition, and what we obtain is that the network is penalizing it less, since the score is already taken down by this fact of the composition being feasible. And this means that at test time, I have a higher chance to predict it. And this is what we would like to obtain. So this is our margins that we have. Like here, we not margins, but actually modifications on the scores. So we have the wet tomato that started from here, the score, and we lower it down. For the ripe dog, instead, we raise the score. And so the network with the cross entropy loss will penalize more the fact of having predicted a ripe dog rather than the score for wet tomato. And we will possibly end up in predicting the right composition. So this is the idea. Now we can use these feasibility scores, assuming that they are bounded between -1 and 1. And now the question is, how do we obtain these feasibility scores? And the idea is that if we have two objects in our dataset, so in this case, a cat and a dog, they are pretty similar, right? And we know from the dataset that maybe some cats are cute and some dogs are dry. Since they are similar, what we can do is saying, okay, maybe since we know that some dogs are dry, cats can be dry as well. And since we know that some cats are cute and cats are similar to dog, also dogs can be cute. Why not? And this is the overall picture. What we practically did was this. So we took the object, the training, this yellow box means the scene compositions that we have during training. And we have their associated states. These are all present in the training set. And then we take an unseen composition, for instance, wet tomato. And what we check is, okay, now which object appear with the state wet? We check the training set and we see, oh, there is dog and there is apple. This is the embedding space, let's say, represented. And we can see that apple and tomato are actually pretty close in this space, in this embedding space. Their similarity is pretty high. And we can just say, okay, the wet tomato feasibility score corresponds to the similarity between apple and tomato, which is the similarity between tomato and the closest object having that particular state, wet in this case, in our training set. And this is how we set the feasibility score. We can do the same for ripe dog. Now, ripe dog, we check, and the ripe is only for tomato. And actually, dogs and tomato are not that similar. And the cosine similarity between their embeddings will be low. And so we can just conclude that they are unfeasible. When I say conclude, is actually, I mean, not exact, just because we keep these scores. So we say that a feasibility score for wet tomato is the cosine similarity between apple and tomato, while the feasibility score for ripe dog is the similarity between tomato and dog. And so this will be very, very low. This will be very, very high. And in this way, we hope that we are able to capture how likely it is for an object to have a particular state. This is what we do object side. We did it also state side.
If we can, 1 second, just something maybe I missed it.
Yep.
When we were talking about the feasibility score of wet and tomato,
yeah,
we actually took the distance between the tomato and the dog into account. But we said that the score is the right because apple and tomato are close without any consideration of the dog. So
yeah, because it's
yeah,
something I forgot to mention is that we take the maximum similarity. So we also compute the similarity between tomato and dog, but this similarity is much, much lower than tomato and apple. And in the formula that we have to compute these feasibility scores, we just take the maximum among the similarities. This is a choice. I mean, the reason is that we want to model the closeness, let's say, similarity between objects.
Okay. And
sorry. No, it can also be another option, may have been like the average, for instance, the average similarity. I wouldn't say the minimum, because the minimum is actually, I fear it can be restrictive and may suffer from the presence of outlier more than the maximum in this case.
You can talk about median also. In this case, it won't suffer from outliers, right?
The median would have been another, like we choose the maximum actually for a reason, because let's suppose we have a data set where we have where wet is associated with apple and with 100 animals, right? Now, in this case, the feasibility for wet tomato would have been low, and because the median or the minimum or the average doesn't capture the fact that there is an object, which is apple, which is similar to tomato, and so the feasibility should be higher. But this is actually, we did it thinking that it was the straightforward and most meaningful things, but probably, I mean, we should have ablated it better. I think this is indeed a good point, like the way you exclude these cosine similarities.
And if you can show the next example, just to see. So we have ripe dog, and in this case, we only have that ripe apple, and then we want to see
ripe tomato. Yeah, sorry.
Yeah, and then we say, okay, ripe dog. Dog is very far from the tomato, so ripeness with regard to him, and he's also very far from apple. But apple, we don't know if he's ripe or not. So okay,
exactly.
Yeah. And while we're on question time, so Yuval had another question. Did you try plugging in the learned feasibility score to the previous GCN approach?
We are currently doing it. I think we will come up with an archive in a couple of weeks because it's indeed something that is linked to actually the previous question, in the sense that the previous question that you, Peter, and I don't know also if Yuval had about having the like, how do you build the graph if you don't have any prior knowledge? And you can really not build the graph if you don't know the unseen compositions, because you will end up in having every connection to be the same, and it's I mean, completely unclear what you expect to learn. In this case of the feasibility, instead, if you work in the open world, you don't need any assumption, like you are not making any assumption. but you can model the weights of the connections. Like you don't say, okay, I don't know, tomato is connected to wet because I have an unseen composition of wet tomato, but tomato is related to wet in a strong way because the feasibility score of wet tomato is actually high. And maybe ripe is not connected to dog because this feasibility is low. We have tried different stuffs. We are currently working on that, and it's really cool. Indeed, also in that case, I can kind of spoil that the feasibility scores help in modeling both the connections and both if applied in the loss and in the model. But yeah, I didn't put anything here just because we are currently working on it. I hope that soon we can show it to the public as well.
Once you have it, if you could send it over also, or just publish it in our subreddit, I guess people will want to see.
Yeah. Once I will share it as soon as we have it online.
Mm-hmm.
Okay, like I don't know if there are other questions. I hope I've been clear in answering.
Yeah, it was perfect. No other questions in the meantime.
So this is our full model. Here I separated between closed and open world because unfortunately, like if you apply what we applied in the open world, the results are not super good in the closed world. And I think I forgot to put it in the slide. Actually, in the paper, you can find the results of the open world model applied to the closed world. It's still better than the other models, but the graph, because the graph is much more powerful than this simple model. But it's limiting. Like it doesn't really exploit the fact that at test time you will see a low number of unseen composition. Here instead at test time we want to predict any of them and possibly catch the right one in this large search space. So these are the results I was mentioning. If applied in the closed world, the results are good. Are actually better than SymNet, TMN. Like some approaches are missing, like Yuval's one because it was concurrent work basically. But yeah, it's working pretty well on mixed states. On Zappos, it's actually lower than TMN for AUC. But yeah, comparable and better actually in unseen accuracy. But yeah, the graph embedding in the closed world is better. This is actually what happens in the open world. So we tried the graph also in the open world, and the performance are actually not that great. I mean, for duty Zappos are great, but in duty Zappos, all compositions are actually feasible. I mean, it's really hard to see maybe a shoe that cannot be made of a particular material or something like that. So the open world scenario in Zappos is actually not that meaningful. We are currently running experiments for C-GQA in the open world, and that is pretty challenging. And for mixed states, though, where the actually is in an intermediate level between being all feasible as in Zappos and having a lot of possible unfeasible combinations as in C-GQA, our CompCos model is very, very good. Actually, it achieves an AUC of 1.6 that is even superior to the one that you would obtain with a naive application of the graph-based approach to this scenario. Not for seen accuracy, but this is expected because this is something you see in the training set. But when you have to extrapolate and to generalize to something out of the training set, actually the difference is large. Like the CompCos is doubling the performance of the graph-based approach and even in harmonic mean. And actually the cosine similarity here helps. Even our closed world version of the model is working pretty well, but not as well, of course, as including the feasibility scores. So yeah, this is what I wanted to highlight. There are some ablations. I will go fast because I think I'm taking much more of the time I had available.
How much about time more do you have left, you think?
No, I don't know. Like we started at 1 is 2:30, so I don't know. Just stop me or wave the hands whenever I'm going over time.
We are over time, but I think it's okay. If there's 10 more minutes, something like this, it's okay. No worries.
Yeah, I'm finishing.
Okay.
We are close. And so just as ablation, if we start with the closed world model and we add already the fact of having at the denominator the full compositional space, so all combinations, without taking into account the feasibility, there is a large jump in performance. So already we go from 1.2 to 1.7 AUC. Including the feasibility score allows to get even better results. So going to 2.0, and actually we added also a warm up because at the beginning the embeddings are not well fine-tuned enough for this scenario. So we hope that while fine-tuning them, we can capture better the relationship and between objects and states, and at the end also the feasibility scores. I said object and states just because obviously you can compute the feasibility scores in the way I described, either using only objects, that is what I've said to you, or similarly we can apply the same reasoning to the states. So given if we want to compute the feasibility of a composition with respect to a state, we check which state has that particular object of the composition, and then we compute the cosine similarity between the target state and the states in our training set containing that object. And then we explored how to mix these two, and the average was working well in this scenario. And we performed also other experiments like, okay, if we want just to not use these margins, but just taking out the least feasible compositions from this output space. One thing that we can do is to just take the feasibility scores and compute a threshold. The threshold is actually estimated on the validation set of the dataset. We didn't find a better way to not use any of the unseen compositions. But let's say you estimate a threshold, and then with this threshold you take out the compositions that are less feasible, and you apply this mask to all approaches. So not only to our CompCos, but also to other closed world approaches. And actually the results are improving. Like here you can see for LabelEmbed Plus, for TMN. The results are not improving from SymNet, and this is interesting because actually SymNet, it's more robust to this open world scenario with respect to other approaches because it's first predicting the object and then the states. So if the object prediction is enough robust, then it's a matter of estimating the states. But all of these other approaches actually predict object and states together, and so suffer more from having this search space enlarged, because now also the object depends on the state while predicting it, etc., etc. These are some qualitative results. So if you look at the feasibility scores of our model, we have something like this, that among the most feasible, we have brown tomato, caramelized potato. Those are all unseen compositions. And we have, I don't know, blunt milk or standing vegetable with maybe some weird genetic modification can achieve that. And also if we look at objects and we print like the most feasible and less feasible compositions per object, we see nice things like, I don't know, winglet cat, but also viscous cat as less feasible. So we were kind of happy by seeing these results. And these are also other qualitative results on the predictions. And maybe I want just to focus on one of them, which I find very funny, which is this balloon. Like our closed world model predicts that this is an inflated egg, while our CompCos model predicts it as huge balloon correctly. And there are also other things which are actually nice. Like if you see, this is some cases where our model is not predicting the right thing, but still it makes sense. Yeah, like some of them do not make sense for our closed world model. Like here there is the scratched cheese, which is not quite right, or a steaming light bulb, which I don't know for where it comes from, while still our model does a good job. Even here, there is an old tiger and it predicts it as young, which is not that nice, but anyway, we were happy. So let's go to the conclusions and future works. I hope I gave you an overview of compositional zero-shot learning and the approaches to tackle this task. I'm sorry for having taken time on SymNet. I hope the authors will appreciate still my job if they watch the video. I showed you how modeling actually the relation between unseen and seen compositions can lead to good results, and also with the primitives. And in the open world compositional zero-shot learning, how actually it's a more challenging problem, and we need to take into account the feasibility of each composition to have this improvement on the results. For future works, there are many. One thing is that the results are still not satisfactory, even with the compositional graph embedding approach that is pretty good in all the benchmark. The results are still low, like 14% on C-GQA for unseen compositions and 28% on mid-states. Open world compositional zero-shot learning indeed is, we tried to start addressing it, but it's definitely an open question. And as well as how to estimate these feasibility scores. For now, we just use this similarity between the embeddings, but maybe external resources may help. Multi-state, multi-object composition zero-shot learning is definitely something that must be addressed. And also, it's interesting how the principles, maybe that of this composition zero-shot learning, both problems and methods, like the symmetry of the embedding space, something like that, may be useful also for other tasks. And this concludes my talk. I have the link to the code, which is not yet activated, but will be activated either today or tomorrow. So it's something that you can check out, and later this week you will find both our approaches, so both CGE and CompCos. Thank you, and I'm happy to take questions.
I actually have a question, a curious one. So the way I understood GCN, and now you also said that you're, let's say, enlarging it with the feasibility score, is that you have to train for the seen and unseen connections, right? The seen and unseen parts of the graph.
What do you mean by you have to train?
You have different, so you have different pairs of states and objects, and the pairs are defined according to the graph, right? Especially on the unseen part, on the seen, of course, but on the unseen part.
Yeah, actually, maybe I don't know if I got it right, what you mean, but it is like vice versa, like the graph is defined based on the compositions that we have.
Yeah, including the compositions that are on the validation and the test set.
Yeah, every composition present in the data.
Yeah,
right.
And after you define the graph, then you, if I understood correct, you got to be training on the different variations of the compositions. Even the ones that are not in the data set, as long as there is a composition that is feasible.
No, you don't, you keep into account within the model, but you don't train explicitly for them.
Okay.
Like it's not that you take images of the validation or test set, of course.
No, not taking images, but you can take, let's say, if you have in the validation an old dog, so it's like old and dog, they have the 3 combo thing going on. But then during training, you got to account for, let's say, old and something, right? Old and all the possibilities, including old and dog, even if you don't have the image of old and dog. So you can have an image of a dog, let's say, and account for old and dog, even if you don't have an image.
Yeah.
So it enlarges your training set, basically, enlarges the amount of training that you have to do, if I understand correctly.
Yeah, actually, it's maybe more on the, it doesn't change much from the point of view of training perspective, just because like it's one can see this graph approach as the LabelEmbed one. So where you have state and object embeddings, and you project them into the shared embedding space where you will match them with image features. What changes is that now your transformation is not a multi-layer perceptron anymore, but is a graph convolutional neural network that takes into account all the embeddings. The training is pretty much the same. It's the transformation that is taking into account all compositions and all this kind of connections.
So this doesn't add any number of computations the more you add different nodes or edges to the graph.
I would guess in terms of flops, yes, because of course you have now more
larger graph.
Yeah, larger graph. But in terms of training time, I don't think so. I mean, from the experiments that I have run also on for including the feasibility scores within this graph approach, the convergence time of LabelEmbed and graph or CGE or other approaches is not that different.
And what, by the way, what was the training time and what hardware did you use?
Actually, it's a pretty, one good thing of this dataset is that they are not that large. Even C-GQA is not that large. So for instance, for Zappos, you can do a full training of any model, I would say in minutes, so in less than 5 minutes. If you don't train end-to-end, if you train end-to-end, of course, the time gets a bit, I mean, grows, but again, it's still a matter of minutes. Like probably instead of 5 minutes, you will take 15, 20, but it's still manageable. For
me, what GPU?
On one GPU, yeah, it occupies very little memory. I mean, of course, if you don't end-to-end, if you end-to-end train, it occupies a bit more, but the networks are ResNet 18. So I performed experiments on a V100, but I mean, it's the memory consumption was actually not covering the full availability, let's say, memory availability of the network, memory capacity. And yeah, for mid states and C-GQA, the time increased, and but it's maybe for C-GQA it arrives closer to 1 hour or a couple of hours. I mean, it depends on the setting, because in the closed world is much faster. In the open world where you have all the compositions, etc., it's a pain validating usually, because it's taking it needs to predict. For C-GQA is 400 compositions, 400,000 compositions, sorry. So it needs to predict every of them, a score for every of them, and it takes a bit of time. But yeah, again, it's nothing serious.
Okay,
I've
cool.
seen a question on YouTube, maybe, on how to, for the access for C-GQA.
Let me see. I don't think. Oh, yeah. Can you please guide how to get access of C-GQA dataset? Yeah.
Yeah, actually, I will. I mean, it will be all included in our code release. We are currently waiting for the code release just because we are uploading the C-GQA dataset, and as soon as this is done, we will have a README explaining how to set it up and work with it. Yeah, it will be straightforward once we release the code. That I hope again that we will do today or tomorrow.
Oh, so if it's today and tomorrow, just send it over and we could publish everything together.
Yeah, sure.
Yeah, so this about this. We had another question. So about the code, somebody said the link seems to be broken. Somebody sent it.
It's not public yet. Like, I wanted to post it here because it will be public. Yeah, whenever other people will watch the video, will find it public. But now it's not. It will be released, as I said, in either today or tomorrow.
There's a question, I'm not sure about it, but let's ask still. On inference, what is the effect of masking?
The effect of masking in inference is that you just don't predict something. It's actually you predict, but you don't consider it in your as possible prediction. So if I go maybe again back. So if we go here, what we do is that we project the features, and this is what we obtain maybe. But then with masking, we say, okay, ripe dog is below this line, so it's below a certain threshold, and so we exclude ripe dog from the output space, and then we predict just things that have an higher feasibility score with respect to a threshold. Honestly, I don't like much this approach for open world. Like it brings improvements, as we have seen in the ablation table, but it requires you to tune a threshold. And tuning a threshold, it doesn't make sense if you don't assume to have some validation or something, or yeah, you can perform, of course, cross-validation, etc. But it's hard to tune, and it's not generalizable, I think, in the reality. So it's better to just go for, to me, for some softer version where you don't exclude anything, unless you are super sure, of course, that something doesn't exist.
And and does it also improve the prediction latency?
What do you mean by prediction latency? It's the time. Oh,
yeah.
Sorry. It's actually no, because I mean, it could in principle, but what we did in the code was faster thing to implement, which is just you predict everything and then you exclude the stuff. Because also your mask may change, and yeah, you don't want to restrict a priori the model anyway. But it can be, yeah, it can be improved. In principle, it can also allow to improve the time, but I'm not super sure about that.
Thanks. You're welcome, Mainak. I hope I said the name right. There's another question, non-technical one by Arun. Can you elaborate a little on connections between compositionality and its implications on explainability?
Yeah, this is actually a good question. To me, it's linked to a lot to maybe what the definition of compositionality that was given by Schmid-Huber. So if we take, let me go to the very first slide. So if we go here, in this definition, what you have is that you have a complex system and you want to decompose it in small parts and then solve one task at a time. And to me, it's a lot interesting, this fact that, I mean, is whatever it's linked to what we do also as humans. Like when we are asked to cook something, for instance, it's not that we just say, okay, robot prepare a pizza, and then the robot prepares the pizza or whatever, and we are happy with that. Maybe we can have the agent or whatever explaining the simple steps that lead to the final result. That can be, in the case of cooking, like having, you know, this the full recipe, and maybe describing the single actions that led to the final result. And with this describing can help in having then achieving, let's say, explainability in what the model did. At the end, if something gets wrong in the middle of the steps, you know where the problem is. Then, of course, like explainability is a wide topic, in the sense that we can have explanations in terms of natural language, in terms of saliency maps or whatever. But to me, is the divide and conquer part that can be that can connect compositionality and explainability. Obviously, it's less clear for compositional zero-shot learning itself, but for more complex tasks, where once you have discovered the primitives, you then make use of this information, that can be pretty helpful. To me, I hope I answered.
Any more questions? Otherwise, everybody will be wrapping up. So 5 seconds, waiting for a question. Nothing. So let me close this. Masi, thank you for joining today and giving us this talk and teaching us. We will wait for you to publish the open source and send it to us also. By the way, if there will be interest, later on we could have a short talk about the open source and how to use it. We'll see how it goes. If you would be available, also if the audience would be asking for it. I will say thank you for all that stayed. We went really long past the time, but still we have people.
I hope you enjoy.
Yeah. We have about 6 people on YouTube still, 13 people here. So I think it was it's a sign of a good talk. And with this, I will say again, thank you, and bye to everybody.
Thank you.
Thank you.
Thanks, guys. Take care.